Okay, so now we're ready to jump into Newton's second law. Now, let me just say to you, uh, there's a lot of stuff going on here. A lot of assumptions are built into this Newton's second law thing that you got to be very careful with. So we're just going to go with the most common way people say this, and for our purposes, that's pretty good. And as a matter of fact, the truth is we don't even use Newton's second law in statics, but I'm telling you, this is one of the few times where you may get an explanation that will allow you to work some of the more complicated problems. And so I want to just touch on this law here a little bit, just so you'll be able to think back on it later and know that you know what's going on. It says if the resultant force acting on a particle, now this is very big here, of constant mass. So there's two things: particle and constant mass. Okay, so we're saying there's a particle here and that there is a force acting right there. So here's a force, there's a particle, like that. And if that force is not zero, and maybe I put a little vector sign on there because forces are vectors. If that force is not zero, then the particle will have an acceleration. That means the particle will begin to accelerate. Now, if it starts at zero, if it had no initial speed or velocity, then it would start to move in the direction of that force with an acceleration which is proportional to the magnitude of the force, and it's inversely proportional to the mass of the force, and so that it will begin to accelerate in this direction, which I'll call A. And if I look at this, I can then say that F, the force, is M is really just the constant of proportionality, and that's A. So the acceleration vector and the resultant force have exactly the same direction. Now, it doesn't matter what the initial speed of the particle was. It could be going in this vertical direction if you wanted it to be. And all of a sudden, I apply a horizontal force. Regardless of which direction it was moving, that acceleration is going to occur in the direction of the force. It has nothing whatsoever to do with the speed of this thing when the force was applied. So this acceleration is a function only of the magnitude of that force, and these two vectors are proportional by this constant m, which we refer to as the mass, you see. And really, the only real way that we have to determine the mass of an object is to do some experiments where, and you may have even done this in the physics lab, where you took one of those air hockey tables and put a puck on there and moved it with a certain force, and you calculated how much the speed was, and so that you could calculate the acceleration, and then you could get the proportionality of that line, and that would be the mass. That's about the only direct way that we have to do it. So F is equal to ma. Now everybody knows about that formula. Okay, but now suppose I want to apply that formula to the space shuttle. Now, those of you that are just now arriving in this class should remember that once, when you were younger, we had a space shuttle, and we shot it into outer space, and we could put astronauts up there. Did you know that? We could if we wanted people to go to the International Space Station, we could put them in the shuttle and send them up there. We're not able to do that anymore. We have to pay money to other countries so that we can get to the International Space Station that we built and paid for, by the way. But at any rate, what I'm trying to say here is that if we actually still had a space shuttle and we put it on the launch pad and we hit the button, what comes out of the back of the space shuttle? Mass, rocket exhaust. Okay, so what I'm talking about here is not going to apply to a situation like that, because that's not a particle and it's not constant mass. And that becomes a much more complicated problem. And through the use of finite difference and a few tricks like that, you could take this formula and work your way to a practical endpoint on a problem like that. But you have to understand that this Newton's second law assumes particle, constant mass. And anything that deviates from that, it doesn't apply. But we kind of loosely translate that to everything that we deal with, and so we don't really have a major argument with that. And then, like I say, where this is really going to show up is when you move into 363. And when you move into 363, some of those people want to tell you that F minus MA is equal to 0. And that's called the Allenby's principle. And it just really destroys your thinking process to do that. So just don't do that. Just F is equal to MA. The force vector, the acceleration vector, they're the same direction. You do it that way and everything is cool. And then I've just kind of listed out F is the force, M is the mass. And see, if you draw a graph that has acceleration and force, the slope of that line is the mass. So that's Newton's second law.